Hello there, Mr. Sutton bringing you this lesson on area between curves. In this one, we will be finding the positive area between a set of curves. So in this lesson, we're going to be using integrals to find the positive area between two functions on an interval. But before we do that, agree or disagree, we've been doing this all along. Well, you might be thinking we've never done this before, but actually we kind of have. So up to this point, we've been finding the area between a function and the x-axis. When you take an integral, you're just finding the area under the curve, and that's what we mean by that. However, the x-axis has a special name. That is the line y equals 0. So when you were finding the integral from a to b of f of x dx, you could have thought of this as finding the integral of the distance between f of x and the line y equals 0, or simply f of x minus 0, because we subtract to find the distance between two things. So we're going to upgrade this a little bit because this is kind of limited. This only allows us to work with y equals 0 as our default other function. And it also has the limitation that if f of x is below the x-axis, we're getting negative area out of this. What if we only want positive area, like a total distance kind of situation? So we're going to do two big upgrades today. Our first upgrade is we're going to be able to use any function instead of just y equals 0. So I'm going to call this area between f of g, and I'm going to say that we've got the integral from a to b of f of x minus g of x. So I've simply replaced 0 with g of x, and now if we subtract these two functions, we can find the area between them. Kind of, sort of. What if f is below g? Then we still end up with negative area. So our other upgrade for this is we're going to use absolute value sometimes to avoid negative area. Now, one way to do that is by putting it around the whole integral. You also could put it inside the integral depending on whether or not you're able to use a calculator. Or you could just not include it at all. It turns out you actually don't even need the absolute value if you know that f of x is greater than or equal to g of x on your interval. So we'll take a look at all different cases today. For our first example, we're going to be trying to find the area enclosed by these curves here. We have f of x, g of x, and we have x equals 1 and x equals 3, two vertical lines. So take a moment and just throw these in Desmos and see what it looks like. In general, it's a good idea to graph these functions to at least see which one is higher up, because that's going to change our order of subtraction if we're not using absolute value. So go into Desmos here. We've got f of x equals 2x squared minus 8x, so parabola. And then we also have g of x equaling e to the exponent x over 5, so we have an exponential function. And then we also have the vertical lines x equals 1 and x equals 3. Now, Desmos is really good at graphing these vertical lines. So you just put in x equals 1, and there's one vertical line. And then let's do another one, x equals 3. There's another vertical line. So the area that's between all of these curves is this region in here. So that's this place. Desmos didn't do the shading, I did, but there it is so that we can look at it. Now, when you're creating your integral, figure out which function is higher up and do the subtraction in that order. But also, if you're looking for limits of integration and they've given you vertical lines, those are going to be your limits of integration. So pause the video and see if you can figure out the area of this shaded region based on what we have here. All right, so going back to Desmos, we'll go in a minute actually. Let me show the setup. So we're going to need the integral here from 1 to 3, and we're going to add up all these distance strips here. So that's going to be, this is the g function up here, and our parabola f is down here. So we're going to do g of x minus f of x dx. Now, if you didn't want to figure out which one was higher up, you could just put an absolute value around everything and just take the positive result. But let's do it this way on the calculator just for practice. So let's see here. Let me go down to another entry. We've got integral int, and that's going to be 1 to 3, and parentheses, g of x minus f of x, close the parentheses, dx, comes out to about 17.670. For this next problem, although it says no calculator, we're going to cheat a little bit and plug these into the calculator just to see what we're looking at. But you could graph these just fine on your own. We're just doing this to speed things up a little bit. All right, so going to Desmos, we've got y equals, I'm not going to bother with f and g and all that. We have y equals x squared plus 2x and y equals 3x. So here's the visual that we're dealing with. And we want the area enclosed by these two curves. Now there's only one little sliver of area in here if you zoom way in. It's this area here that we're dealing with. So this is kind of a visual of what we're up against. Now we have to do this without a calculator. We have a top function and a bottom function. However, we may need to solve a system of equations with these functions in here in order to find these two limits that are bounding off this function. So with that in mind, pause the video and maybe do that and see if you can find this without a calculator. Okay, so I'm going to set these equal to each other. We have x squared plus 2x equals 3x. And then if I subtract 3x from both sides, I've got x squared minus x equals 0. And this is going to be pretty easy just to factor out an x. That leaves us with x minus 1. And we see that x is going to be 0 and 1, which we could see on the graph. But again, we weren't really technically allowed to use a graphing calculator on this one. So this is another way we could have arrived at those numbers. So at this point, I'm going to need to take the integral from 0 to 1 of, well, I would be doing 3x minus this x squared plus 2x. But one thing I'm going to do just to kind of shortcut this process, I've actually already subtracted these two functions when I solved this system and got everything on one side. I subtracted them kind of in the wrong order. In this case, we have, basically parabola minus line, which is going to give us some negative area if I integrate this. But I'm going to put all that in an absolute value to take care of that mess. So I'm going to do the integral then, the absolute value of the integral from 0 to 1 of x squared minus x dx. And now just taking my antiderivatives on this, this bumps up to a 3 and to divide by that, so we've got 1/3 x cubed minus, this is going to be 1/2 x squared, and we're integrating that from 0 to 1. So I've got all this stuff with 1 plugged in minus all this stuff with 0 plugged in. And this is almost kind of comical. I mean, we've got 1/3 minus 1/2. These ones just kind of go away. And then over here, everything is getting zeroed out, so I don't even need to worry about that. So then we just have the absolute value of 1/3 minus 1/2. And we don't have to simplify it. We actually didn't have to simplify it even up here. But if we were to, this is like having 2/6 minus 3/6, which is negative 1/6. But the absolute value turns that into a positive 1/6. For our last problem, we're going to go back to the calculator. So if you like, you can guilt-free plug these in your calculator and see what it looks like. All right, now when I do that, here is what I end up with. So we've got f of x equals negative 3 sine of x. Good, good. And let's do now g of x equals the square root of x. And here's my situation. Now if I go over to the right a little bit, I see that there's really only two bounded regions. This region in here and this other region. So we've got just two bounded regions. Now the trouble with trying to use one integral here is that we have a change in which function is higher up. So we're going to have to deal with that in a second. One thing in general, just a general tip on this, is when you have these intersection points, it's not a bad idea to store those intersection values as constants on both your paper and on the calculator. So let's, when you go ahead and find out what those intersection points are, maybe just consider making them constants. Like I used P and Q, you could use A and B, whatever you want to do. Strategizing what else you're going to do with those constants though, because we have these two different areas. One option is to split your integral up and change your integrand when the top and the bottom functions change from one area to the next. So that's one way to do it. Now, obviously, that could be kind of annoying if you have more than 2 of these, if you've got like maybe 5 of these different areas because of this sine function going back and forth. So another option of dealing with this, and this is kind of like when we were finding the total distance traveled by a particle and didn't feel like finding every little direction change, you could instead just use one integral with absolute value inside. So that way, no matter which way we were subtracting, we would always get a positive distance strip to add together. So pause the video and choose your own adventure on this one, and then we'll bring it back together to see how it went. All right, so I'm going to figure out where these functions equal each other. So f of x equals g of x, where? Well, let me go on my calculator and find those spots. So we've got 0, obviously, but we're not worrying about that. We also have 3.855 and some change, and we also have 5.397. So I am going to cut and paste both of those. I'm going to let this first one be called P, and this other one here, this 5.397, I'm going to call that one Q, so Q equals. So now I've got those stored and can use them. So I just did at x equals 0, that's also one of my values. And then we've got P, which is our first one, and Q, which is the 5 one. So if I want to split the integral, my first integral, we're going to be going from 0 to P, and that is going to be the square root minus the sine function, so g of x minus f of x in there. Our next integral would be from P to Q, and then that would be, in this case, that would be the sine minus the square root, so f of x minus g of x. And we can plug all that in on the calculator. So let me go ahead and show you all of that plugged in. So we have integral, and let me just get down there, 0 to P, and I've already stored P, and then parentheses g of x minus f of x, close parentheses, dx, and we're adding to that another integral, int, from P to Q. This is why it's nice to have those stored, and then parentheses f of x minus g of x, dx, and all that comes out to 11.167. All well and good. So that's one way to do it. Again, this is kind of cumbersome if you've got lots of different areas. So if these just keep kind of switching back and forth, another option is you could just do the integral from 0 to Q, that last point there, and we're just going to do absolute value of f minus g or g minus f. It won't really matter at that point. Just pick one and go with it. So just going back to Desmos to see if we get the same answer. We've got integral from 0 to Q, absolute value of f of x minus g of x, close the absolute value, dx, and we again get 11.167. So that's it for this one. I was going to come up with a parting joke, but the area in my head is coming up kind of blank right now. Till next time, Mr. Sutton signing off.